pH, weak acids, and dissociation. So we're going to be talking about pH again, and this time we're going to be solving weak acid equilibrium problems. We already talked about solving strong acids, but now we're on to the ones that involve a Ka value. So this is the general way to solve these problems. You're going to list the major species in the solution, then you're going to choose the species that can produce the hydrogen ions, and we want to make sure that it's the stronger of the two acids. Using the values of the equilibrium constants, decide which equilibrium will dominate, and then write that equilibrium expression for the dominant equilibrium. List the initial concentrations of the species participating in the dominant equilibrium, in other words, kind of like ice, you're going to use the I. Define the change needed to achieve equilibrium, that is, define x. Sometimes we have to leave it as x, and sometimes we actually know what x is. Write the equilibrium concentrations in terms of x, substitute, and you're going to subtract. And eventually you're going to get the equilibrium concentrations, at which time you will plug into the equilibrium expression. Solve for x the easy way. Remember, you're going to use the 5% rule to subtract out minus x. You're going to verify that it can be done that way, and then you're going to calculate hydrogen and pH as a result. So let's look at an example here. Consider a 0.80 molar aqueous solution of the weak acid HCN. You can see that it has a Ka value of 6.2 times 10 to the negative 10. What are the major species in solution? What is there that's contributing to the hydrogen ions? Well, HCN and water. Now you might think, what about hydrogen and Cn negative? It ionizes slightly. Why isn't it a major species? Well, that's exactly the reason. Doesn't ionize very well, so there's very little hydrogen or cyanide in solution. So that's why the only two things are HCN and water. You then have to look at the Ka values of these two. Now, Ka value for HCN, as you can see, is 6.2 times 10 to the negative 10. Not a very big number, but the other choice is water. You can see that the Kw for water is 1 times 10 to the negative 14. And you notice that HCN's Ka value is still bigger than that for water. So, which reaction controls the pH? Obviously, that which is in the HCN. So let's get on to some problem solving. Calculate the pH of a 0.5 molar aqueous solution of the weak acid HF. And that Ka value is 7.2 times 10 to the negative 4. So how do we do it? Well, we think about the major species in solution. We know HF and we know water are two of the major species. Certainly not hydrogen or fluoride ion. And that's because it doesn't ionize well and form those ions. What are the possibilities for the dominant reaction? So we look at the Ka values again. You notice that HF is significantly larger than the Kw. So that's the one that controls the pH. So we're going to solve for the pH. Now you notice we're writing the HF, which is the major species that dominates the pH with water. It's going to be acting like an acid, so it gives its hydrogen away to form hydronium and fluoride ions. The initial concentration, as the question stated earlier, was 0.5. We have no products. And the change, we don't know. And you can see here a traditional problem, minus x for the reactants and plus x for the products. Essentially, we're going to put products over reactants. And when you do, you're going to get a Ka value of 7.2 times 10 to the negative 4. Thus, the pH is 1.72. You actually have to be given the Ka value, and then you solve for x. When you solve for x, you get H3O, and then you find the negative log of it, which in this case is 1.72. Another concept you have to remember is dissociation, or ionization, how well things break apart into positives and negatives. How do we get percent dissociation? Well, we have to take, it's like part over whole times 100. the percent dissociation is the amount dissociated, molarity, over the initial concentration times 100. For a given weak acid, the percent dissociation increases as the acid becomes more dilute. This is an important concept because weak acids do not ionize well. They only ionize a small amount. So if they're weaker, they're going to dissociate a certain amount. And if the concentration is less, that means the dissociation is going to be greater. Very strong concentrations of weak acids will only dissociate the same small amount. So when you do the division, a smaller number over a greater initial concentration is going to produce a smaller percent dissociation. So here's a good question. A solution of 8 molar formic acid is 0.47% ionized in water. Calculate the Ka value for formic acid. Alright, how do we solve this problem? Let me find my pen and show you how to do that. Alright, now we know the Ka value is going to be products over reactant. So if we write the equation out, HCHO2, and when it breaks apart it's going to form hydrogen and CHO2 negative. Now I could have added that to water and gotten hydronium ion, but I decided not to. And it's because water isn't part of the equilibrium expression anyway. So eventually I'm going to have to do products over reactants. I really don't have enough information to know the value of X. I do know initially we have an 8 molar and I don't have any products, but I don't necessarily know the change, and I don't know the Ka value, so I can't solve for hydrogen or anything like that. So what do? Well, I know the percent dissociation is 0.47. So what I'm going to do is I'm going to use that formula, 0.47 is equal to the percent dissociation of the hydrogen over the initial concentration times 100. So when I solved this, I actually got 0.0376. And then, from that, I can calculate the Ka value for the formic acid. So how do I do that? Well, pretty easily, because products over reactant, you notice 0.0376 is the change column minus 0.0376, which won't make much difference. And when I do products over reactants, or 0.0376 over 8, and this is going to be squared, I get the value for Ka to be 1.8 times 10 to the negative 4. I actually got a little bit less, but rounded to 2 sig figs, I did get 1.8 times 10 to the negative 4. Now, if I want to calculate the pH of the 8 molar solution of formic acid, how would we do that? Well, now that we know the Ka value, it's pretty easy. I'm going to figure out the value of H, which I already knew, which was 0.0376. So I take the negative log of it, and I get a pH of 1.42. Let's look at this question, also about formic acid. And here's a question that says the value of Ka for a 4 molar formic acid solution should be higher than, lower than, the same as the previous one. The value of Ka for the 8 molar. We just on the 8 molar one, we got the Ka value. What about a 4 molar solution? Should it be higher, lower, or the same? Well, remember, Ka value is a constant. So let's see what we get. Oh, shockingly, it's the same, because it's a constant for a particular situation. Dissociation will be different, but the Ka is going to be the same. The percent dissociation of a 4 molar formic acid solution should be higher, lower, or the same as the percent ionization of an 8 molar formic acid solution. Let's figure that one out. So the percent ionization of a 4 molar formic acid solution, what do you think? It should be higher because remember, formic acid doesn't dissociate well. So if the concentration of the overall acid is lower, a greater percentage of those particles will be ionized. So actually the percent ionization is going to be higher. The pH of a 4 molar formic acid should be higher, lower, or the same as that pH of an 8 molar formic acid solution. Again, higher, because pH depends on the hydrogen ion concentration. If you have a lower hydrogen ion concentration, you're going to have a higher pH. Calculate the percent ionization of a 4 molar formic acid solution in water. How do we do that? Well, we're going to set up another ice chart again, and here's the answer, but let's figure out how to do it. So we have our equilibrium from before. I'm not going to write it out again. I'll just call it formic acid yields hydrogen ions and some negative A ion. Initially we have 4 molar. We don't have any products. Minus X plus X, X, 4 minus X. And we want the percent ionization. In other words, what is X? So we're going to solve, and we're going to get X squared over 4 minus X, which I'm going to get rid of, the minus X, and that's going to equal the Ka from before, which was 1.8 times 10 to the negative 4. Now when I solve all of that, I get my X value to be 0.0268. That's the concentration of the hydrogen ions. Well, of course, that can help us in percent ionization, because we need that over the original times 100. In other words, 0.0268 over the original, which was 4 molar, times 100. And we can see what percent of the ions went through the arrow and dissociated. And when you work it out, you do indeed get 0.67. How about calculating the pH of a 4 molar solution of formic acid? How do we do that? Pretty easily, because if we know the percent dissociation and we know the hydrogen ion concentration, which was 0.0268, from before when I solved Ka, I just take the negative log, and when I do, I get a pH of 1.57.